So, thank you for coming here, and thank you for inviting to do a small talk about the Live IP software toolkit. That's what we produced at EBU, and it's open source, so that's the good part. And sorry, I have to show you the next slide here as well, but this is actually the reason why we did it. So when we talk about the European Broadcast Union, it's about broadcasters. So normally you saw, well, antennas and that sort of things, but lately, of course, it's also about webcast, podcast, and that sort of things. So for those guys, it's a big change. Of course, not for you guys. So usually I present this type of presentation for broadcasters saying, well, this is probably the biggest change in 30 years after going from PAL to SDI. SDI, that's a professional format to transport video. And now we want to move from this SDI specific format into an IP format for our professional broadcast plant. Now that's interesting because higher management always speaks about, well, this SDI cable, we need to rip it out. If we want to move from SD to HD or UHD, each time we need to break out everything and start from scratch. And those are long projects. So actually we want to have some sort of flexibility to move from one format to the other format as soon as we can and as soon as needed. Or maybe go back as well. So this is why we say, well, IP for us is like a container ship. If we put in SD, HD, VR, whatever type of audio format, it will work. On the other hand, as broadcast engineers, we were very proud because in the 90s we had 270 megabit per second as a professional format, and IP was at 10 megabit per second, so we were very advanced. But now, of course, due to the scale of the industry, we see switches of 32 times 400 gigabit per second. If we do the calculation back to 720 P60 formats, you see that we can have 10,000 video streams in 2 units instead of multiple racks 48 U's high. So that's a nice advantage for broadcasters to go to IP. Shareability, that's another story because we're not there yet. Shareability for a broadcaster means, well, we want to run everything on generic hardware. And this is exactly why we did this Live IP software toolkit. Now, to give you a little bit of the insight on the industry, this is a very interesting roadmap. Who has seen this before? That's very good, right on track. So this is our SDI technology, and we wanted to move to IP. A few years ago, they said, well, let's take all the SDI, we wrap it into IP, and we transport it. But actually, that's not what we need to do, because SDI is encapsulated with audio, video, and ancillary data. So if you just do that, that's a waste of bandwidth in a video plant, because you need to de-embed and embed all the time all the ancillary data and the audio. So then they said, well, let's go to elementary streams. Let's put the video part, the audio part, and let's flow all those streams through the network. And of course, we need to synchronize them again. So we use the standards within the IT world, IEEE 1588, the Precision Time Protocol. Now, there are a few standards in this, but not to bore you with all these 70 documents. There's a very interesting one, -21, and this one talks about the traffic shaping of those packets over the network, and that's the important part, and also the part where some politics are coming in. So, there's another part as well. Who has a device at home that uses SDI? Whoa, that's a good room. That's a really good room. Most of the time, everyone, even if we do this course with broadcasters, nobody shows his hand. And the reason why I ask this is, of course, well, SDI is very secure because you could almost say it's security through obscurity. Nobody has it. And on the other hand, don't forget that SDI was damn reliable. You plug it and it works. Well, with IP, you need to have an IP address, of course, and that sort of things. So there's a little bit of work on the road. And this -21 document that talks about traffic shaping is just a key element of moving with our professional media into the IP space. So, if we talk about this, reliability, it's just to talk about the network, so let's dive in. This you all know, but it's an important slide because, well, for data, timing is not critical. For media, it damn is. And if we miss a pixel somewhere in the video, maybe you didn't see that we missed a pixel. That's a hard message for real video engineers, but voilà, c'est comme ça. Interesting, you can dive into the difference a little bit more, and you see, well, you have the circuit-based networks, like our SDI, and you have packet-based networks, specialized for data. But this is the important part here. We can move towards that sort of networks for professional media. The only thing we need to take care of is the packet delay variation. Now, packet delay variation, it sounds all very easy, so what can it do? It can lead to increased latency, but also dropped packets. And this is exactly where the small detail where we want to focus a little bit. So I'll try to run you through this packet delay variation in a quite easy way, I hope. And I like to compare it with this nice racetrack. This racetrack, as long as the gray car is up front, I would say this is perfectly behaved traffic. Now, what will happen when the gray car disappears? You will have, this is what I would call bursty traffic. Now, the real IP guys will say, no, this is collision, but sorry, it's not a collision domain. I just want to say it's bursty traffic. Now, another thing that broadcast engineers don't perceive when an IT guy says something about bandwidth, the IT guy says, well, you're consuming 32 megabit per second or whatever. But by saying it's megabit per second, it's averaged over an amount of time. So the broadcast engineer thinks, oh, there's a packet, there's nothing, there's a packet, there's nothing. Equally spaced. Well, in reality, it's of course not. Now, on a single lane, who cares about this? But of course, a network is just not a single lane. A network is more than this. Oh, by the way, average speed, 55 miles an hour, let's say. But if you have birds, you use the link speed. Packets could be so close to each other that you use the link speed. So, multiple lanes. So let's try to compare it to traffic, I would say, but actually the comparison stops here. Because in IP networks, when you go to a reduced set of lanes, well, instead of going slower, you should go faster. Otherwise, it's a little bit of, it's just a waste. So this is the type of networks we're talking about in our video plans, spine leaf networks. And imagine there's hosts connected and there's an interlink between the spine and the leaf of 40 gig. So as long as you don't have more bandwidth here than you have here available, we could say this is a non-blocking network, and imagine all this ECMP stuff in the middle is working perfect. So we can balance packets instead of just streams. Imagine. This means for our broadcasters that we have, for instance, 12 cameras connected on a 10 gig link, so 12 times 1/3 the bandwidth. That equals 4 times the bandwidth. So in theory, this all works pretty happy. Now, of course, when I say there is something like packet delay variation, of course you have another issue. Because in reality, we connected 120 gig to a switch and we want an uplink of 40 gig. So there's an issue. And especially if the traffic is bursty. Because at the end of the day, you're starting to use the buffer of the switch. By the way, you never know how the switch buffer memory is allocated. It could be sliced in 4 parts and copies could be made because you're using multicast and that sort of things. So at the end of the day, there's a small packet that's probably not happy and not welcome in the buffer and needs to be dropped. And this is exactly the space where we don't want to be. Now, this is actually the space where vendors do want to be. And this is a huge political discussion we had because of this. The closer you are with your implementation, and not pointing at anyone, but assuming an FPGA implementation, the better you are at pacing your packets on the network. If you have an operating system in between and your application on top, you're less in control. And we think about virtualizing our IP facilities. For broadcast, that's quite far off. So this is why we were interested in the standard to tweak a little bit those packet delay variation numbers, because they wanted to make it so specific that only FPGA implementations were allowed. So where would you go with open source? That's an issue. Another part, I just plugged it in because I had something flipping in my mind that say, hey, we're using UDP, we're using multicast. So actually we cannot make a non-blocking network. We need an SDN controller. You can imagine a situation where you plug in just another receiver and suddenly you start using more bandwidth between spine and leaf than you have available. That's the way the IP network should work, but it's a bit of an issue for a broadcaster. So this already demands for an SDN controller. Okay, I promised to talk about traffic shaping, so let's dive in. This SEMT guys, they did understand it, so they say we need something to control this traffic shape, so we define virtual buffer models. And it's nothing more than a funnel. It's like when you want to throw water in a bottle, you use a funnel, you do the water in, and when it overflows, of course, then you start to drop packets. And you've been using this in the IT industry for many years, so nothing new for you guys. On the receiver side, they define something similar. It's called the VRX, the virtual receive buffer, that needs to be measured at the sender side. It's quite the same as this network buffer model. One exception, the packets are read out of the buffer according to the PTP timing. This is where the fun comes in. So what I just said, we have the CMax buffer model to protect the network. And then let's dive into a little bit what is actually meaning. So this model says it's draining packets onto the network as a function of its video format, and it's just dumping it. And when we say where we have more than 3, let's say 4 packets possible in this funnel, you get a result on your switch like this. So I'll run you through this graph because it looks a little bit complicated, but it's not. This is an egress capacity of the switch of 3.2 terabit per second, a memory of 16 megabytes, and we say we have a Cmax in this funnel of 4. This means if we use the switch for 10%, up to 80% of the traffic of the switch, there's no problem at all. When we go to 90%, there's just a small patch that if we load this fully and in the baddest situation, we start to drop packets. Now some guys say to me, well, Willem, this is just an old switch. There are new switches. I mentioned this before. There's a 12.8 terabit switch per second with 64 megabytes of RAM. But the ratio between the egress capacity and the memory is the same. So the equation just results in the same situation. The only difference is, of course, you have more streams that you can run through the switch. Now, if you would say we move from this FPGA implementation towards a software implementation, which is a little bit more jittering, it could burst up to 16 packets in that buffer, then you could see something like this. Quite interesting, right? 90%, not good. You're starting to drop packets anyway and your application will fail. Now the nice thing is, the higher in resolution you go, you get more into the greens. And that's quite simple. This is an application of UHD, 120 frames per second. So the amount of packet rate and data rate is higher, but you have just 58 streams. So you have to divide your memory between 58 streams, so each individual stream can jitter a little bit more. It's quite easy. So the VRX buffer, I mentioned this before, it's similar like the C buffer, but you need to have PTP simulated to really see what it does. Now these numbers are defined, and this was the biggest struggle in the SMPTE, on the SMPTE calls, and it's this Cmax. And they said you have a narrow sender, which is strictly defined and shall not go above 4 packets in this virtual buffer, and you have a wide sender, which shall not go above 16 packets. And at that time, they were just defining a number because they could, and there was no real implementation in software, and those guys had their NDA signed with switch manufacturers, so they know how the buffer works. But actually, this was too small for software, even the 16. And I'll try to give you a visual overview of that. And again, we're here. Well, in order, if you buy something, this is usually for broadcasters, if you buy equipment, you need to measure this. And there's no test and measurement equipment on the market today that does this. So this was the right spot and the right place for open source and for us to come up with something just to tease the market a little bit. Well, I explained this and this as well, so I'll go over it. So where did we start? They were defining the standard, so I said, well, let's use Excel to try and figure out how all of this works, and of course Excel, well, that's not your best friend if you have this amount of data. Then somebody told me, well, you can use Python, there's a PyShark library and use that and you're good. And then I went to some interrupt tests and there were 60 devices, and Python is nice, but it's a bit slow. So then we asked somebody to write a C++ optimized program, and this is actually how it started. And then we discovered something else, because our broadcast engineers, they're used to this screen, and the IT engineers are used to the other screen. Well, good luck with Wireshark if all the packets are passing by just for one stream on 3 gigabit per second. You don't see a thing. And good luck with this, by the way. you don't know what you're looking at either. Well, no. So we need to bridge those worlds, and this is exactly where we started. Well, that's another example. I'll skip through it. And how did we do it? Well, first we said, let's take just the TCP dump. And the TCP dump we upload through our, oh, no, I'll skip this. So we take a TCP dump to produce a PCAP file. The PCAP file we upload through our GUI, and it just gets to the PCAP store. When it's in the PCAP store, we say, start the middleware, and then we use a stream preprocessor to run through the PCAP file. Because in order to calculate the model, we need to know what it is. Is it a 720p? Is it YCBR? And that sort of things. And actually, most of the things you can find in the stream, but for a few others, like YCBR, you need some heuristics to guess what it is. So that was already a tricky one. Because those guys defined, well, let's use SDP, but they didn't say how to give the SDP. So some manufacturers give you the SDP file via, I kid you not, via email, and some use other mechanisms. Then the next thing, of course, when we have these static data, we put it into the MongoDB, and then we trigger the middleware again, and then we look through the time series of data, and that's why we use the InfluxDB to put it there. Now, that looks pretty basic, so let's show the GUI a little bit. So this is actually what the heuristics does. It looks into the PCAP file, it says, oh, there's an audio stream, there's a video stream, and we find some PTP data. And we try to make it very simple, like if it's green, it's probably okay. If it's red, there's something wrong. The heuristics show up in some more details about the video file, and on the right-hand side, it's pretty small, but it actually says if it's compliant with the C buffer model and the VRX buffer model. Now, to give you a visual, this is a very good one. Very strict. There's at maximum 1 packet in this C buffer. That's very nice. And on the right-hand side, you see the reflection on the Excel grid I showed before. Let's see if I have a nice one. This is a nice example of another one. This is the virtual receive buffer, and this is a TCP dump we got. And the guys didn't know why their solution was breaking, but actually it's very, very simple because you have underruns. There are no packets in the buffer when the application needs to read the video frames according to the PTP clock. So those are the VRX underruns, and actually we can run through frame by frame and exactly see, it's on this frame, what happened. You see the typical green line. There's no data available to reproduce the picture. And it's a collaborative project, so we joined the CBC colleagues from Canada, and they said, well, we're actually implementing audio over IP, and we see a lot of issues. They wanted to have low latency, and that's an audio profile with 125 microseconds, so that's really low latency for in-ear monitoring. Otherwise, you have a comb filter effect, and it's not easy to sing. So they wanted to see the jitter for audio. And 10 years ago, there was a model written, TSDF. We just implemented it, and it matches perfect with the IES67 spec. And it's all open source. So what did we see? Actually, for this application to work, we just need a precise timestamp with a nanosecond granularity. And the timestamp must be given on a network interface card as close to the NIC, to the Ethernet jack as possible. And of course, it needs to be synchronized with PTP. I'll skip this one, and I show the latest development with it. What I told you right now is just offline, so you need to have a TCP dump and do it. Last 3 weeks, we were a little bit we dove into our lab. On the left-hand side, you see our PTP generator, a switch, some SDI senders, a prism, and that sort of things. But on the right-hand side, you see something simple. That's a NUC. Well, it's a powerful, we don't need such a powerful beast. And this is just an empty cradle. We plugged in an Ethernet board. It's connected to a Thunderbolt. And actually, we cannot just do a TCP dump. We can have the precise measurements live. Open source, nothing special. The difference of this box and another box that you buy on the market, well, it's about 58,000 euro. À peu près. So to be sure that we have good results, we also looked at the jitter of the clock and the resynchronization of PTP4L, how that worked out. And then we did a capture with those official high-grade boxes and with our cheap man's box. And it seems that we're pretty close to all the other captures. So I can say really confident that our live implementation is precise as possible. If you want to know more, there's a URL, TechEBU/list. Of course, there's the GitHub. And for real broadcasters that are not into, well, I need to CMake and all the things with the code, we do have a Docker container as well. And if you don't dare to do that, we just have listebu.io, which is the virtualized version of our tool. Any questions?
So earlier on, when you were mentioning spine leaf architecture, what's the entry like in terms of the headers? Is it just one? Hello. Is it just one flow? You need both. Yeah. Is it just one flow between one producer and one consumer, and therefore does it hash well across the entire network if you're doing ECMP?
No, the problem you could have is, well, normally when you have a live production or you have somewhere a production, someone at the end says, oh, I need to have a monitor there, will you plug it in? Well, you don't know what the bandwidth is you're using. Maybe you're already using, well, in that example, theoretical example, there were 20 receivers. Just if you plug the one extra, you need to, well, you subscribe to it and you get it. But the bandwidth is broken for everyone. So all the receivers will just get stuck.
And a small follow-up question. Do you know what the average kind of frame size is for the UDP transmissions? What the packet size is?
It's normal. It's 1500. Well,
okay, so it's the full frame
so it's not jumbo frame size.
No. Okay, thank you. Yes, Kieran.
It's interesting you talked about the TSDF, timestamp delay factor for audio. Have you done any work on how sort of multiplexing of the audio and video works in practice with some receivers, especially receivers which are not timestamping the audio but just playing it through? Well, there's a few of those as far as I've noticed. Have you done any work on how senders should multiplex the audio with the video? Because obviously there's a very precise timing model for video, but there's not a model for how a sender should multiplex the audio with video. Obviously the hardware senders send it spot on, but as a software sender where the audio is being processed somewhere else, so usually the video is done with kernel bypass and the audio is done with sockets. What actually matters in real life with regards to the multiplexing?
Well, that's a very good question. And we're just up to the fact that we virtually produced different levels of audio. So we have level A, B, C, and AX, BX, and CX with 24 bits, 48 kilohertz, 96 kilo. And all of those we created, and then we made them a little bit variable as well. So we have good examples and bad examples, and that's the next step is to run them through pipes and load pipes, because this is what we didn't do yet, because we don't have enough material or equipment at the moment to really load the switch. But in theory, you could also calculate that whatever just switching through the network, you have an impact already on the low audio profile. So.
One last question. No?
I got them all to sleep, sorry.
No, you were crystal clear. Thank you, Willem.
Thank you. Yeah.